Section 4.7 continues with our discussion of aqueous solution reactions, with talking about different parts of the reaction and ways to kind of discover what the truly important parts and what the less important parts are for the reactions that we're observing. Now there's three stages really to talk about what takes place in solution. We have the molecular equation, which is what we've already been using. This is where we show everything. If things are whole molecules or ionic substances, we show them together as one piece, and we show all these little states of matter and that sort of thing. Now the total ionic equation is where we break all ionic bonds, none of the covalent, just all the ionic bonds, everything that's soluble. There are insoluble compounds, and we break these bonds and then show the individual ions that are formed on the reactants and products side. Then after that, we kind of go through and we take out just the ones that are actually doing something and list those separately. So what we look for are only the things that actually change between reactants and products. Everything else we refer to as a spectator. So let's take a look at this. We'll have a description, and we're going to have to describe this reaction first using the molecular equation. That's our first step. So we have aqueous lead 2 nitrate, lead, nitrates -1, so I need 2 of them. It says it's aqueous, or we could look at that from the solubility rules that we've memorized. Reacts with aqueous potassium chloride, +1 -1 is a 1-to-1 ratio. Reacts to form a yellow solid substance in an aqueous solution of ions. Alright, so let's do what we did in the last section. Lead, iodine +2 -1. Iodides are all soluble except for lead, silver, and mercury, so solid. And all nitrates are aqueous. And now we balance. Uh-oh, chloride. Where did I get iodine from? Excellent. There we go. Alright, so 2 chlorines and 2 chlorines, 2 potassiums, 2 nitrates, 2 nitrates, 1 lead, and 1 lead. Okay, so here we go. Here's the balanced molecular equation. Next, we want to break this down to the total ionic equation. So we look at what we'll break apart. This says aqueous, so we break it apart. Lead and nitrate ions. The nitrates themselves stay together because those are covalent attachments. Okay, so aqueous, so that means this breaks apart. So potassium and chlorine. Solid, this does not break apart, stays together. Potassium nitrate, it says it's aqueous, so potassiums and nitrates break apart. So let's break this down. We have 1 lead +2 ion, which is aqueous. We have 2 nitrate ions, which are aqueous. They're separated from the lead, so they don't stick together anymore. We don't want to write something like this. Okay? That is not what you want to write. You want to show those nitrates as being individual entities, which they are. So this 2 coefficient goes in front because of that subscript in the original formula. We have 2 potassium ions, which are aqueous, and 2 chloride ions, which are aqueous. Sometimes you have to turn the paper sideways to do this stuff. It's so obnoxious. Right, so lead chloride solid. It's solid, so it all stays together. 2 potassium ions from this, and 2 nitrate ions, aqueous, from this, and there we go. That is our total ionic equation. And there we have the total ionic equation. Now for the net ionic equation, we just look at what changes. So lead becomes lead chloride. The chloride's part of that. But the nitrate ions stay exactly the same, both sides. And the potassium ions stay exactly the same on both sides as well. So that means that what we're looking at here is really just lead ions and 2 chloride ions becoming lead chloride. But that's the net ionic equation. Because that's the only thing that's really changing here. The potassium ions float around and the nitrate ions float around, but they're not really attaching to anything differently. And they're pretty much exactly the same as they are from when they were in an aqueous solution as potassium chloride and lead nitrate. In fact, any lead salt that's soluble and any chloride salt that's soluble will have the same net ionic equation. Now we mentioned spectator ions before. Spectator ions are any of these that don't actually change. They're just spectators to the reaction. So in this one, potassium ions and nitrate ions are spectators. That sums that all up pretty directly. And that's it. That's how this works. Let's have you try one. So pause this, give it a try, and then we'll come back and talk about it. Okay, so I'm assuming you gave this a shot at this point, so let's translate. Sulfuric acid, potassium hydroxide, sodium sulfate, liquid water. Okay, so let's put those in equation form. Aqueous, potassium hydroxide, sodium sulfate, and liquid water. Alright, so that's the total, that's the molecular equation. That's all the molecules and their states of matter. So we break this apart. 2 H pluses, which are aqueous, and 1 sulfate, polyatomic anion, aqueous. We should probably balance this as well here, so it's, can't believe I wrote sodium. What is it about these products? I'm doing too many examples here. There we go. So potassium sulfate. So I need 2 potassiums, and that's going to give me 2 hydroxides and 2 of those. So we need 2 of these. Now we have 4 hydrogens. 4 hydrogens, 4, 5, 6 oxygens, 4, 5, 6 oxygens. Good. All right, so that's balanced. 2 potassiums and 2 hydroxides. Okay, this is aqueous, so 2 potassiums plus a sulfate. Okay, so this is a liquid. Pure liquids and solids do not come apart. So 2 liquid waters. And that's our total ionic equation. Now we'll look at the net ionic equation. What stays the same? Well, sulfate stays the same, so that's a spectator. Potassium stays the same, so that's a spectator. So in reality, what we're looking at here with sulfuric acid and potassium hydroxide is two hydrogen ions and two hydroxide ions form two water molecules. And in fact, when we report this, we want the simplest whole number ratio. So we just say H plus and OH minus make water. This is actually the net ionic equation for all of these ionic acid-base reactions, which we go into a little bit more in the next section. So spectators, potassium ions, and sulfate ions. You don't have to give numbers or ratios of these things. We're just saying that this species, chemical species, is a spectator, and the sulfate chemical species is also a spectator. So that's all there is to it. I've confused it. Slide. That's usually before I start. And now I can write okay. That is not it. Okay. Come on.